Well, thank you for the kind introduction, and of course, thank you to the organizers for inviting me here. It's my first time at ICTS and my first time in India, so I'm very happy to be here. I've been having a great time so far, and I'm hoping to have another second week. That's going to be great. Okay, all working, great. Yeah, so I'm going to talk about kind of correlation dynamics in these dipolar multilayers. There's not going to be a lot of Floquet stuff, but I added 2 slides on Floquet. So there will be something that is actually relevant to the topic of the workshop as well. So let me briefly talk about why I'm kind of care about these systems. So this is kind of an experimentally AMO motivated talk. The reason why I like AMO systems is that they kind of give us the capability to custom design and control a quantum system in kind of a Lego putting things together sense. So kind of going from kind of the capability to control quantum particles at the single particle and single site level, we can control kind of what kind of particles and the statistics that we want to put into our quantum systems. We can, to a large degree, control what kind of interactions these particles should experience. And we can also selectively prepare product states or more interesting quantum states in these geometries that we can also tune. And then finally, given the topic of the workshop, we also have kind of temporal control over these systems. And what that allows us to do is to kind of generate kind of highly tunable, in my talk, kind of long-range interacting spin models, and then tune them via kind of spatially temporal control to explore kind of coherent many-body dynamics of some interest to us. And specifically, I will kind of talk about 2 specific applications. So I will kind of explain how we can get 2-mode squeezing in kind of these dipolar multilayers. So that's about generating methodologically useful forms of entanglement. In the second part, I will kind of talk about how we can use the single site control to actually get a twist to the story where we'll kind of talk about momentum entanglement in these spatially separated bilayers. So let me briefly kind of give you an idea what kind of platforms I'm thinking about. So there's kind of a wide range of experimental systems where we get long-range interacting spin models. So I've kind of put a few references here. For this talk, most relevant are kind of the first 3 kind of examples, which is kind of polar molecules, magnetic atoms, or Rydberg arrays. And more specifically, most of what I'm going to talk about was motivated by polar molecules. So what kind of matters for this talk is that they give you a kind of long-range 1/cube interactions with kind of dipole with kind of some anisotropic kind of character. And you can boil all of that down in a kind of simplified setting to saying I can reduce it to a spin-1/2 manifold of these polar molecules, and then you get kind of long-range interacting spin models out. So specifically, they kind of take the form of kind of XXD models where there are kind of coupling constants Vij between, say, some confined sites in an optical lattice, and then you will have an XX kind of a spin exchange term and a kind of JZ easing term. And that kind of will be the setting I'm going to consider in the following. So in addition, in these settings, there's a variety of kind of beautiful experiments that actually make possible what I want to discuss. So there's one experiment that actually was involved in kind of polar molecules where they actually show how to prepare these multi-layer structures. So specifically what they do there, they kind of have an optical lattice along the Z direction and then apply an electric field gradient which kind of splits the internal level structure in a layer dependent way. And that then allows you to do pair state preparation in these systems as well as spectroscopically measure these layers independently. So I'm happy to talk about more about the details of this experiment kind of offline. So this is just to say we can in principle do this. There's another great experiment in the catalytic group where they do it with magnetic atoms. Again, they kind of have an optical lattice. In that case, they use 2 different polarized beams with slightly different frequencies, which then also allows you to essentially generate kind of these stacks of bilayer structures that have dipolar interacting atoms, magnetic atoms in this case, in them. And then you can also put them in tweezer arrays, and if you have tweezer arrays, you can essentially generate any geometry you like. So it's kind of a beautiful experiment where they kind of demonstrate on-demand entanglement of molecules in these tweezer arrays. So this is kind of on the spatial control side. You can also observe them. So there's another beautiful experiment in the Bakker group where they actually kind of look at polar molecules and kind of use a quantum glass microscope to really measure the 2-particle correlations in this system on a site-resolved basis. So with that kind of having told you that in principle all of what I'm going to talk about is possible to do the experiment, let me tell you what I actually want to do. So I want to kind of create these kind of multi-layer structures. In this case, I kind of illustrate kind of putting polar molecules in there. There will be 2 spin states. And what I want to do is I want to kind of create a staggered pattern where, say, I have them in alternating up and down states initially. And then I want to use the interactions to essentially create a very large spin, which kind of initially points in some direction. I want to use the spin exchange interactions between these layers to essentially create a spin exchange or a pair creation mechanism. And that then actually creates an SU11 kind of Hamiltonian that gives you entanglement generation. So kind of to break that down a bit, so this is kind of the model. I kind of now put my layers that are kind of on top of each other, next to each other. One will kind of stay in an excited state, the other layer will be prepared in a ground state, and we have kind of interactions kind of between the layer and kind of within the layer. And the full Hamiltonian is just this kind of long-range kind of XXC-like interaction Hamiltonian, now written for kind of lattice-confined spins. And as I said, there's these two terms. At the moment, it's kind of a generic XXC model. It's just kind of pretty complicated. So I want to make my life a bit easier. Let's imagine we go to the Heisenberg point. So imagine the Z interactions are the same as the V per interactions. In that case, at the Heisenberg point, this model actually becomes fully SU2 symmetric. And let's, for this moment, assume that our interactions are long-range enough, that they are mostly collective. In that case, this pair Hamiltonian actually just uses the S dot S. And what that gives you is that you kind of create a gap between the collective Dickey states, essentially all states with a lower spin length. In that case, you can project down your full Hamiltonian into the collective limit. So let's do that. In that case, I replace my small spins kind of with large collective spins, and I replace my interactions with average interactions. And this is now a Hamiltonian that I can actually understand the dynamics of. So starting from this Hamiltonian, the first term, if I start in a collective initial state, is just a constant. It gives me my gap, but it won't kind of change the dynamics at all. And the second term will now give me the dynamics I kind of want. So this is this interlayer spin exchange. And since it's now a very large spin, I can perform a Holstein-Primakov approximation to a very quantitative level. So I replace my spin operators with bosons, kind of an A boson for one layer and a B boson for the other layer. And then you will see that the spin exchange exactly maps to pair creation. In addition, we will have kind of an Ising term that creates a detuning between these layers. And what you then see is that this full Hamiltonian, many body Hamiltonian, actually just maps to two-mode squeezing. We still have a detuning term. So the detuning term we can cancel by essentially applying a field gradient or essentially any kind of term that covers to the Z field of your spins. You can use it to cancel it, then we just get pure two-mode squeezing. And so why might you care about generating two-mode squeezing? So I've kind of told you start with this very complicated many-body spin system, and now I've told you it maps to quadratic bosons. So one of the reasons why you might want to do that is, well, it's a lot easier to do, so you can understand, and it actually exponentially generates entanglement. It's also a process that is kind of mean field, kind of completely static, so it's a purely quantum phenomenon in that sense. And in this case, we can kind of create it in kind of molecules or atoms, so there's no photon loss or motional decurrence in principle. So this is kind of the story just from the bosonic level. So does this actually work in practice? So why do we care about two-mode squeezing here? So maybe a bit of background. So there's the other reasons why you might care about that. So at least in the last talk, Ollie introduced the SU11 kind of Hamiltonian. That's essentially the same way, a different way to talk about two-mode squeezing. Essentially, you could think about this parametric amplification or two-mode squeezing in quantum optics. You can also relate it to kind of effects in high energy physics. So this pair creation process also underlies kind of the Springer effect or Unruh radiation, which you can actually then use to quantum simulate kind of accelerated space-time. We already heard in the last talk about the thermophile double state. It turns out that this kind of dynamics also generates thermophile double states, which you then can use to kind of make connections to black hole quantum teleportation protocols, or you can use them for EPR steering. So there's kind of a lot of motivation to be able to kind of generate these kind of Hamiltonians in a large system. And what I'm going to talk about here is kind of a bit simpler, so break it down to something we can actually measure. So what does the two-mode squeezing Hamiltonian do? So it generates kind of, if you apply to a vacuum state, it kind of generates this kind of thermophile double state with structure NN in layer A and layer B with some prefactor. And it turns out that the number of pairs you create is kind of exponential in time with this squeezing parameter. At the same time, it generates a squeezing in mixed quadratures. So essentially, if you look at spin operators kind of coupled between your layer A and layer B, you will see that one direction essentially gets squeezed while the other kind of gets anti-squeezed. And that is why it's metrologically useful. So if you now ask, can I measure kind of a rotation of this spin distribution? You can measure it more precisely because this distribution has been squeezed. And again, this generation of entanglement is also exponential in time. And you could ask, does this actually happen in the full quantum system? So what I'm now going to do is I'm going to do simulations using kind of a semi-classical phase space method, so specifically discrete truncated Wigner, to simulate the full many-body spin dynamics of the system, starting from exactly the state I told you about. And what I'm showing first is kind of just the number of pairs. So this is essentially the magnetization in these layers, kind of in a gauge invariant way where I kind of count how many pairs I've created as a function of time in a logarithmic plot. And the kind of dashed silver line is just the two-mode squeezing exponential prediction. And kind of we see that for large enough system sizes, say 1600 spins in each layer, we kind of nicely see this exponential growth roughly up to square root of n particles that I've created. And we do understand why that happens roughly around square root n. That is both the curvature of the Bloch sphere and also the fact that I only cancel the layer detuning at the 0 pair level. So the other important thing is that I told you we have to stay in this collective state for all of that to make sense. So you can tune that a bit by changing the layer kind of spacing. So I just make my layer wider spaced. In that case, you see that what I show is essentially the spin length of my full many-body quantum system actually stays very, very close to n squared, which means I actually stay in a fully collective spin. So I really map perfectly to collective pair creation or two-mode squeezing in this setting by tuning the parameters that I in principle have access to in the experiment. So this was kind of pair creation. I also told you that I generated squeezing. So you could ask, does this actually happen in practice? So this is the plot of the variance of this operator as a function of time, again on a logarithmic plot, compared to the silver line, which is the two-mode squeezing prediction, which kind of just exponentially goes down. And you can kind of see that if your layers are widely spaced enough, you nicely follow this kind of exponential prediction down to the not quite Heisenberg limit, but the square root n limit, where we said we see kind of corrections due to the curvature of the Bloch sphere. So we kind of do see that this model can be mapped to collective spins, large spins, and we do see we can create kind of collective entanglement in these systems in spatially separated bilayers here. That can also be used just using collective measurements. So I can talk about how you would actually use that to kind of create a metrological protocol offline if you are interested. But the point here is that we can create these very nice kind of collective spin states using dipole interactions. On the full Hamiltonian, it's the full Vij kind of spatially, yeah, that's correct. Of course, in the collective model, all of that would be pretty simple. Yeah, then you could just do exact dynamics because it's a Hilbert space of size n, and then it would be very easy. And that works out the same way. Yeah, and also these square root n corrections show up exactly the same way in the collective model. Yeah. So then let me briefly kind of talk about kind of exactly this question. So one of the things you might be worried about in experiments, it's not always a fully collective kind of nicely unit-filled lattice. An experimentalist might give you something like this. So there's some random positions of these particles, and then you could worry it's maybe not very collective. So what I'm going to say is this is kind of a slightly different way of plotting this kind of variance in terms of taking a log of it. And it does go down, but even for like 50-ish%, even then it's relatively stable. And the way you can understand this is that actually, say the XY model in a single bilayer, there's a phase transition to synchronization that Nigel worked out, I think 5 years ago. They're kind of all these XY spins, even if they're filled with about 10%, there's actually synchronization transition where you kind of go into a collective state. And that's one of the reasons why I believe this actually works even at moderate filling fractions. So this is what I wanted to talk about the first part. Now I want to do a bit of Floquet. Sorry. So can we do better? Can we do better by using temporal control of the system? So we started kind of from some kind of collective model that had Heisenberg interactions within the layers and Heisenberg between layers. I told you I need the Heisenberg interactions within the layer to kind of protect my collective spin state to then get collective entanglement. But I really don't want the Ising term between layers. So ideally, I would use some protocol that just gives me spin exchange, which is my two-mode squeezing Hamiltonian just between layers. So I want to kind of engineer my dynamics to be adapted to the spatial state that I've created. And you can in principle do that. So this is kind of a way to do it in kind of this toggling frame picture. So what I'm showing here is kind of the interaction, the SD spin in the interaction frame. So essentially, I imagine performing pulses that kind of toggle my spin, rotate my spin along different axes. For the upper level in the layer 1, for the lower level in the layer 2, and then I just literally just move my spin around in rotations around x, y, z. And if you do exactly this protocol, and then you kind of choose a different sign in kind of the reverse protocol between layer 1 and layer 2, you can cancel the Ising interactions between layers. And then you exactly kind of generate this type of Hamiltonian in the high frequency approximation to this Floquet protocol. So if you do exactly this, you can actually do better. So if you then start with this Floquet Hamiltonian, so what I'm comparing here is again the number of pairs versus time and the squeezing versus time in Dash without doing the Floquet protocol, in solid lines with the Floquet protocol. And you kind of see you can extend this regime where you get this nice exponential collective scaling of the entanglement generation in this system. So that's what I wanted to call Floquet. Let me talk about the second part, which is essentially about using this spatial selectivity in the system to kind of use this capability to measure these two-point correlation functions. So what we're going to kind of asking here is, okay, given that we have these bilayers, maybe not fully filled, and this access to two-point correlation functions, is there interesting dynamics that we can either see in the spatial dimension or in the momentum space picture for these entangled pairs that I create? Again, it's kind of the same kind of model. We start with these bilayers with kind of one layer in the excited state, one layer in the ground state. And it's the same model. It's again a long-range XXC spin model. But instead of going to the Heisenberg point, as I did in the first part, we're going to go to the XY point. So in this case, we're going to ignore kind of the Ising interactions and just look at the XY model. And of course, in this case, I don't have Heisenberg interactions that protect me. So this dynamics will generically not be collective now. So I can't go to a large collective spin, but I can just go to momentum space. So let us kind of take this model and just take the Fourier transform, or well, I guess first do the Holtzman-Primakov. So now I actually have small spins. And these are now hardcore bosons. So I use these hardcore bosons in this model and then go to momentum space. In that case, what you see is this model of kind of a spin exchange in these bilayers kind of maps to some momentum space pair creation process, where the intra-layer interactions, the exchange between the spins in the same layers, maps essentially to a dispersion, which is the Fourier transform of my intra-layer interactions. And the spin exchange between layers maps to this correlated pair creation process. It is the Fourier transform of the inter-layer interactions. This Hamiltonian might already be pretty familiar to you, depending on what your background is. So let's see what we can do with this kind of Hamiltonian. So at this point, it's quadratic, but it's written in hardcore bosons. So this is still an interacting model. But let us ignore that those are hardcore bosons and just do the typical Holtzman-Primakov and ignore the higher order terms. In that case, it's a fully quadratic. So it's definitely not okay for the long-term dynamics when you create many pairs. But essentially, the hardcore nature shows up once kind of you create a population that is large. And at that point, it will not work, of course, which is why we then have to actually then again do simulations to see what we get. So this will now be the analytical part to understand what we might expect to see in the full simulations. So generically, it is not true that this works, for sure. But for now, assuming it is a quadratic Hamiltonian of non-interacting bosons, it's a quadratic Hamiltonian, you can just solve it in terms of Bogoliubov transformation. And what you will see is that the quasi-energy can become imaginary. So it's kind of this typical square root form where the dispersion and the pair creation term, and there's a minus sign between those two. And exactly where this becomes imaginary, I'm going to create these entangled pairs. And you can kind of nicely see this. So if you look at the Briot zone and you kind of look at the strength of the pair creation in color plot and overlay this thick line is essentially the zero of the dispersion, I will kind of create these quasi-particles exactly at these points where this vanishes and the pair creation strength is large. And this is where I create these entangled pairs. And how could we see this in an experiment in the full simulation? So we again see this exponential growth of these quasi-particles now in momentum space. And we can observe it by just measuring the spin structure factor. So mapping the bosons back to the spin operators, the momentum space population just maps to the spin structure factor of the system. And to give you an idea exactly of this question, does it saturate? So this is now a plot of the momentum space population in the unstable mode as a function of time. The dashed lines are the Bogoliubov predictions. And there is a regime where it just goes exponentially initially, where it's valid. And beyond that, we kind of see a regime where we see kind of saturation. And then we see thermalization at the very end. So we kind of go through a three-step regimes in time in the dynamics, where we see actually this hardcore bosons also a spin system, where this description then fails. But there is a regime where we actually see this exponential growth of these entangled pairs. Right, and you can also look at the same way in the momentum space picture. So at very early times, they essentially are dominated by oscillations. So these are kind of typical quantum dynamics quadratically. Then there's an immediate time regime where we see this creation of this exponential creation of these unstable pairs along these lines in momentum space. And then these modes start growing, but I also see less unstable modes that kind of keep growing exponentially, which then eventually scatter and then get thermalization at very, very long times. And then kind of all the structure is gone in the system. And that's the point where essentially we reach kind of a fully unpolarized state in each layer. So the nice thing is we can actually fully tune this momentum structure as well. So depending on, we have some tuning parameters in the system. So what I can ask is if I change the dipole axis of my dipoles compared to the confinement axis, I can actually access kind of different topologies of the pairs I create. So I can kind of create kind of nice circles. If the dipoles are kind of just pointing out of the plane, then I have kind of a symmetry in the plane, which then gives me these kind of nice circles. I can kind of go to other points where I kind of get more like arc-like structures in momentum space. This again compares the Bogoliubov to the DTWA simulations, and they kind of match qualitatively and also quantitatively, both for time scales and the pairs I create in the system. So what we really see, we kind of get this nice kind of quantum simulation of this correlated pair creation with a momentum structure, which you can tune. And I want to emphasize again that all these kind of plots essentially correspond to the creation of entangled pairs in these spatially separated bilayers. And to kind of drive that point home a bit, I could also have told you all of this as quantum simulation of Unruh radiation. So if you kind of just look at this kind of Hamiltonian quadratic in bosons, you can kind of look at the dynamics, you can solve it, and essentially you get kind of a boost-like transformation with these typical SU11 form or these cosine hyperbolic, sine hyperbolics between your time-evolved operators and your initial operators. And if you look at this matrix and you kind of know a bit about quantum field theory and accelerated frames, you can realize that this is the very same matrix that kind of controls how you transfer into an accelerated frame from the vacuum frame or the non-accelerated frame. And then that actually creates particles. As you accelerate in a field theory, you create particles. And this is exactly the same kind of particles we kind of create in time during the quantum dynamics. Right, and then maybe just to kind of wrap this part up, you can in principle also look at all of that in real space. The momentum space structures are kind of slightly nicer, but if you measure in real space, you can also see that kind of you actually generate kind of long range kind of correlations in this system during the time dynamics. Let me briefly talk about this as well. So I told you a bit about this kind of tunability. So what I'm showing here is again this unstable manifold with the most unstable modes kind of marked in these stars for kind of different dipole orientations. So this is kind of, if I change dipole orientation, I can go from these circles to these arc-like structures. And they have a different tuning knob, which is the interlayer spacing. So I can also kind of tune the spacing where then can go to point-light structures, which gives me kind of full control over where I want to kind of create these entangled pairs in momentum space by the parameters that I can easily experimentally access. And finally, all of this is also, again, kind of robust to finite filling fractions. So if you kind of go to an experimentalist and tell them, you know, I have maybe kind of 10% filling, it doesn't look quite as nice, but in principle, it still works. So you can see these kind of structures in momentum space, even at 10% filling. So it's actually feasible to do this in an experiment. So what else can we do? So this was now all about bilayers. Can we do more if we go to multi-layers? In principle, it is kind of natural we ask, what more can we do? And what I essentially told you is that if we have these nice kind of collective interactions, I can create a large spin. So you could ask, okay, I can now create kind of arrays of kind of a large spin. Or alternatively, if I look at it in the bosonic picture, I can kind of engineer two types of terms. I can generate normal tunneling, and I can create this pair creation term that we actually heard a lot about in the last talk. So in principle, now I have the building blocks to kind of create a Kitaev chain. We have this, not correlated topic, this pair creation term. You could also think about kind of slightly different states, and then, you know, it's a dipolar system. So you get dipole conservation. So you could also talk about kind of fracton physics in these kind of systems. So what I want to do in the next part is kind of a bit more humble. I just want to start from the upper Hamiltonian and ask if you have both these kind of pair hopping and the normal hopping term, is there something interesting we can get out? So what I'm going to convince you of that we can get from spin spirals to chiral Kitaev models in this system. So how does it work? So imagine you have kind of these layers. So this is now kind of a slightly different illustration. Each of these large spins corresponds to one 2D layer. And I'm going to prepare a spin spiral, a non-coplanar spin spiral, where each of these layers points along X, Y, Z, and then repeats periodically. So it's like a Z3 spin spiral. And starting from kind of just kind of Heisenberg interactions, if we go kind of to the gauge frame of this initial state, you kind of generate kind of a term of kind of spin mixing interaction where you kind of have xz, yx, and zy interactions. So that is where the chirality will come in. So I've kind of now gauged the initial state chirality into a Hamiltonian chirality. And then it turns actually out that the mean field dynamics are exactly solvable. This is kind of a cute fact. So I'm not aware of many non-trivial mean field dynamics for an interacting Heisenberg spin model that you can solve. This one you can solve exactly, and you get kind of perfect Z3-like oscillations forever, which then also means you can kind of go into a periodically time-dependent frame of exactly this kind of periodic oscillation, which then gives you remove all spin dynamics. And then you can, again, do Holzham-Primakov, and you actually get a bosonic Chiral Kitaev model out. So this is also something that our last speaker actually looked at a few years ago. So after this mapping, we get a bosonic version of, so it looks a bit like a Kitaev model, but those are bosons and not fermions. So it's slightly different, but you can believe me that this actually gives you chiral transport. So specifically, if you kind of look at the equations of motion of this kind of model, you can either look at it again at the spins or at the x quadrature. So I can look at the A plus A dagger and A minus I A dagger kind of combination. So the quadratures of these bosons, and it turns out that the x quadratures only talk to the x spins to the left or below, and the y quadratures actually only talk to the y quadratures above or to the left, right. So these should now show chiral transport, and you could ask, can I actually see that? And that actually is a bit more difficult. So what we looked at is actually the spin-Green's function. So if imagine I kind of have one spin in the central layer at the initial time, and I perturb this spin direction alpha, and I'm asking how does this perturbation propagate to a different layer, side j, in the spin component beta, and I look at this commutator, and I'm asking how does this actually behave in this system. And if I look at the spin-Green's function to the right of my initial layer, I will see that all the response I'm getting comes from an x perturbation. If I'm going to the left of my layer in blue, then all the response I'm getting this side actually comes from a y perturbation in my central layer. So you can kind of see this chiral spin transport in this many body spin system. And there's kind of lots of other things that one can talk about in these multi-layers and the other properties of the chiral spin Kitaev model. So with this, I wanted to summarize this part of the talk. So I have a bit more time, so I might actually talk about another project. So what I've kind of want to convince you of is these kind of dipolar multi-layers are pretty cool in terms of exploring kind of many body dynamics. I talked about two kind of applications. One about kind of generating entanglement that is actually useful. And the second thing about kind of creating these kind of momentum space entangled pairs. To give you a bit more reason why one might to do that. So kind of outlook, what else you could try. So we now have these entangled pairs. It turns out that two-mode squeezing immediately also violates EPR inequalities. You can essentially do Bell tests in these spatially separated bilayers. You could also kind of ask about time reversal protocols that actually do a full SU11 interferometric setup in these bilayers. And current work is kind of looking at thermalization behavior in these systems and non-equilibrium universality. So I told you for everything I've talked so far, these kind of models kind of don't care about the filling fraction, but you could wonder if you actually get localization dynamics in these systems, if there's something like MBL. And this actually work by a Munich group that actually looked at MBL in these two-dimensional structures with one of our cubed interactions. So for this part of what I want to kind of thank the people that were involved. There's references, something in prep, there's my website, but maybe I have a bit of time to talk about another project. So right, this is kind of very, very different. So this is kind of work with also with the Dipolar group, with Michael, Bhuvanesh, and Anna Maria. And this is about kind of trying to use, again, kind of instabilities or dynamical resonances to look at the quantum dynamics of strongly interacting particles in a synthetic flux ladder. So essentially fractional quantum Hall physics. So in this case, it's Hubbard model. So you imagine we have a 1D kind of chain of particles. We will put fermions in there. They will hop from side to side. They have a spin degree of freedom. So there will be tunneling between these lattices. We will have some normal Hubbard interaction between the up and down spins. And we will add a laser drive, which then essentially gives you spin orbit coupling. And that is what gives us this synthetic flux. So this is kind of in the real space picture. You can also understand that in the synthetic dimension way, which is a slightly different way of looking at it. So essentially the laser drive kind of creates a flux if you hop around the full plaquette of the synthetic lattice. It's kind of a very old idea. I think the first one 2015. But that's kind of one way of understanding. So essentially, if my particle hops, then the laser drive at the next size will have a slightly different phase because there's a running phase from the momentum dependence of my laser beams. And that means if I jump across the full plaquette, there's actually a flux that I enclose. And that in practice can be large. So it can be pi or up to 2 pi in practice in the experiments. It can really create a synthetic system with a large magnetic flux. And then to kind of understand the physics of the system, we kind of have to go through a few basis transformations. So there's the lab frame where this hopping phase is in the coupling. You can go to a gauge frame where I put the phase that the laser has into the tunneling. And then I can diagonalize these change independently, and I can put this phase essentially in the hopping matrices where I go to a diagonal frame where the non-interacting hopping Hamiltonian is fully diagonal. But I put the phase now, I pay the price of having tunneling that both couple the same spin states, but also couple different spin states. And kind of doing that, we can now kind of understand what we want to do. So imagine I have very, very strong interactions. So the Hubbard interaction will be large compared to the tunneling, but actually be comparable to the drive. And then you can create essentially bound states of particles or resonances in this following form. So you have the spin conserving tunneling, which will be kind of energetically allowed if there is another particle, but it will be suppressed if there wouldn't be more particles. So essentially this becomes an insulator in this case. But if you actually allow kind of resonances, so imagine I tune my Hubbard U to be the same as my driving frequency, I actually allow this correlated tunneling process where I can create these doublons in my system. And you can also create higher order resonances where you cannot create a doublon, but you can create a triplon at a slightly different resonance frequency. So we now have a system that we can control where we can create multi-particle states in the dynamics of the quantum system. We can actually see those dynamics. So if you kind of ask, if I start in an initially polarized state and I look at the population, the up state versus time, you can kind of see a simple tunneling resonance. You can see the j squared over u, which is the creation of kind of doublons, and you can say the j cubed over u squared resonance, which is the creation of these triplon bound states. And you can also do it as a function of phi and u, and then you kind of see this nice kind of resonance plot, which you can also see in the experiment. If you just look at the long time population as a function of this frequency, you kind of see very clear resonance structures at fractional frequencies. And I don't want to kind of make this analogy too strong, but it kind of already looks a bit like fractional quantum Hall in the sense we see kind of fractional resonances. So this was all for spin half. You can kind of play the same game with SUN fermions. So imagine instead of 2 internal states, I will have n internal states. And you could imagine then it gets even richer because I have more internal states to play with. So let's do that. So let's skip this part. But essentially, I now extend my synthetic dimension to not have 2, but kind of n of these internal levels, which all experience this plaquette flux. I again go to this diagonal frame where this tunneling now becomes non-diagonal and covers all state. And I again play the same game that I'm asking, do I get these resonances of many body bound state pairs? So now we have, as I said, very many potential resonances. We get the normal one, omega u, we get 1 at u half and 1 over u third, essentially by jumping a larger number of internal states. And we again kind of ask, if I start with a fully polarized state, what kind of dynamics do I see? Do I see these resonances in the system? And you can do that. Again, you can plot it as a function of the flux and this frequency, and you now get kind of, again, a kind of resonance structure. If you plot it as a cut, you kind of see now many of these resonances, right, at fractional values, 3 over 4, 3 over 5, 3 over 7, kind of a whole zoo of these fractional resonances in this system. And again, we can understand it in terms of these resonant pair creation process of these multi-particle bound states. And that's kind of now looks very, very close like a fractional quantum Hall kind of idea. Let me kind of skip that, acknowledge the people that kind of did this work, and then maybe go back to my original slide about other stuff I did. So there's always other things I'm interested in that I'm super happy to talk about. I kind of did a lot on kind of classical chaos, hydrodynamics, and analysis scaling in spin chains. With that, I think 5 minutes, I can actually stop for questions.
So questions?
Hi, nice talk. In the first half with sort of the pair creation and spin states, I'm trying to make connections between that and sort of spin mixing, spin squeezing experiments. And I guess the key difference is how important is the fact that you kind of have these two reservoirs creating the pairs rather than a central reservoir that the pairs jointly come out of.
Right.
Like, what's the differences?
Right. You could imagine, I have a single large spin and just do one axis twisting where I just squeeze my, say, JZ squared operator. So one difference is it happens in the same ensemble, and in the same ensemble, you typically are not going to have single particle resolution. They can really resolve in a spatially selective way where the entanglement is. So one clear advantage is we here create them in spatially separated layers. So that then allows us to do things like EPR tests with a kind of collective large quantum system. Another just difference between one-mode squeezing and two-mode squeezing is that two-mode squeezing actually can give you up to Heisenberg scaling. So you can get 1/n scaling out, which you don't get just in one-axis twisting. There's also a question in time scales, like one-axis twisting doesn't proceed exponentially. So you could also ask, is the time scale here actually better? In the sense that if you have sources of decoherence, you could wonder, doing it exponentially fast might be an advantage. Yeah, then there's another difference that in practice, right, if you have a large collective spin, it is only sensitive to a field that comes to the collective spin again. In this case, we have kind of differential measurement because we have kind of two spin ensembles. So you can now measure differential phases rather than sum phases. Yeah.
In the first part, have you thought about if I go to next order in this Holstein-Primakov, what happens to these things? I mean, it might not be easy to probably do, but what is the, if it is a 1/s expansion?
Right. I mean, of course, at that point, you get interaction terms, which generally we cannot solve, right? So at that point, it's kind of hard to make an analytic statement. But the simulations I showed do everything, right? It's the spin model that are simulated. So those in principle take all orders into account to the level that you believe the DTWA simulations. You can, of course, solve so if you actually were to go to the fully collective model, you can solve it exactly because it's an n-level Hilbert space. And we've also compared with that. It actually compares very, very well. So these corrections actually don't matter as much in the collective limit. That's something I can say rigorously. And we also now have kind of work in 1D, where we also do exact dynamics. And again, there, the exact dynamics match very, very well what we predict from Bogoliubov and what we predict from the DTWA simulations. Yeah.
Can you explain one more time the transformation that unwound your spin spiral into the Kitaev? Like, my question is, why isn't the Kitaev chain Hamiltonian not time dependent after you did it?
Right. That's exactly the point, that this is an exactly solvable point of the mean field dynamics, which as I typically don't know many systems that you can actually solve exactly, even classically, right? So
intuitively, how can I think of the absence of time dependence?
Right. So essentially, I start here from the fully Heisenberg model, and I kind of put this initial state dependence into, say, the frame. Right. At this point, if you now ask, okay, in this frame, every frame points along Z. That's the gauge transformation I did here, right? So I now have a Z spin at I+1 and at I, right? So the spin, this X spin feels a Z field, right? So it wants to rotate, but there's one at the other side that kind of also wants. So essentially, all the spins want to rotate in the same direction. So mean field, like, that's exactly what I'm showing you. So this is the Z spin, the X and Y spins, and kind of all of the spins, because you get kind of a torque from both directions, they kind of lead to a fixed rotation axis doing it, and then all of them just rotate. And this global rotation that is fixed in time, I can just gauge out. So essentially, that corresponds to a field that is just SIX plus SIY plus SIZ at every side.
Right, and does this give you an effective fictitious force in the co-moving frame or not?
Exactly. Yeah. So at this point it has a force in the co-moving frame, and now this transformation, right? It is only given by the total spin, which commutes with Hamiltonian. So the U dagger HU vanishes, and this is only the I U delta U is what cancels the field. Exactly. And then you kind of go through the math and you get the Kitaev model out. And if you didn't do that, then the problem is, right, that your frame actually rotates. And then this boson would be a very, very bad expansion, right? Because my spin kind of rotates away. So that's why it's important that we can actually have an exactly solvable point to do this. Yeah.
Thanks.
If there are no more questions, let's thank the speaker again.